Okay, let's talk about, now that we've spent some time thinking about and working with scheme, let's talk about recursion. So recursion is the tool that we use to get repetition to work in our scheme programs. And I'd like to take a moment to think about the fact that there are different kinds of recursion that we might use to solve problems. And it's helpful to be aware of some of those kinds of recursion. So first of all, I'm going to give you a little bit of code. All right. So for int I equals 0, I is less than n, I plus plus. And I guess we're going to say I is less than or equal to n here to make this work. All right, I plus plus. All right, and I'm going to have a sum. Let's set that up here. Int sum equals 0, and sum equals sum plus I. Okay, so what does this program do? This short program do? Well, this is another way of saying sum I equals 0, n of I. So it's a sum of the numbers from 0 up to n. Okay. Now, if we were to think about the impact that this program has on the stack, does the stack use increase as this program runs over time? Does the stack use stay the same, or does it decrease? All right, what are the choices? We're using more of the stack as we run this for loop, we're using the same amount of the stack, or we're using less of the stack? Well, the answer is we're not really using very much of the stack at all when we do this. There's a little bit of stack here for that variable I, and there's some stack being used for the variable sum. But other than that, we're not really using the stack for anything. So the stack basically remains the same. All right. Well, let's see if we can convert this into into Scheme. All right, we're going to convert this program into Scheme. So first of all, we can't use repetition because we can't use iteration like a for loop or a while loop or a do while loop because that's not allowed in Scheme. So we have to use recursion. So I'm going to say define sum of n as a function, and I'm going to use my trusty con statements here. Con, and if n is equal to 0, then I'm done. So if we say like sum of 5, we're going to say that's a way to think about it is sum of 5 is 5 plus the sum of 4. Sum of 4 is 4 plus the sum of 3, and so on and so forth. Okay, so when n is 0, we're just going to return 0. That's our base case. And otherwise, we are going to say, well, all right, I'll just do a shorthand of this. Instead of doing else, I'm just going to say is greater than 0. If n is greater than 0, then we're going to do the following. We're going to add n. So like sum of 5 would be 5 plus the sum of 4. So this would be the sum of n is n plus the sum of n minus 1. Right? Okay. So let's go back to our stack question. As this thing executes, does the does the stack get used or not? And the answer is, this version of sum, do we use more of the stack, same amount, or less of the stack when we run this? Well, the answer to this is we use more of the stack. Let's take a look at our code here. All right, so I'm going to have that. Well, hopefully you have that in your notes. I need some space to make this next part work. So the sum of 5 is 5 plus the sum of 4, which is 4 plus the sum of, oops, I see what I did here. I gotta fix that. 4 plus the sum of 3, which is 3 plus the sum of 2, which is 2 plus the sum of 1, which is 1 plus the sum of 0, which is 0. Okay, now that's the sequence of calls that are required to allow the recursion to trigger the base case and complete our work. Now, as these calls are executing, stuff is getting put on the stack, right? So the sum of 5 is 5 plus the sum of 4. So we need to remember that 5. The sum of 4 is 4 plus the sum of 3. So we need to remember that on the stack. And the sum of 3 is the sum of 3, or is 3 plus the sum of 2, 2, 1, and then we're here at 0. I guess we don't really need to remember the value. Well, I guess, yeah, we do. We're going to return that value of 0 to the caller. So, all right, maybe we'll leave it like that. And this is the original call of sum of 5. Okay, so this is our stack. Now, these values, this 1, 2, 3, 4, and 5, and a placeholder for waiting for the, oh, I guess that 5 is really part of this one. So these placeholders here are indicating the values that have to be remembered, not forgotten, in an expression that's being evaluated to compute the number. Well, if we look at this 5, for example, the sum of 5, we're partially computing this expression. We figured out that part of the expression is a 5, but we need the sum of 4. So we're going to save that 5 on the stack, and then we're going to compute the sum of 4. That saving requires some stack memory to be associated with it. And so if you were to say, like, how much stack memory gets used when we're computing the sum recursively in the way that we've just been in the way that this particular function is written, the answer is it's order n, where n is the number of where n is the value that we're computing the sum up to. All right, so if n is 1,000, that means we're going to have to save 1,000 different values on the stack in order to compute the result before we can get the result computed. If n is 1,000,000, we're going to have to save 1,000,000 values on the stack. So there's a lot of numbers that are getting saved when we do this computation. Now, if we go back up to our original program in C++ or Java, this for loop saves 2 values on the stack, just sum and int. And the more that loop runs, it doesn't really change the number of values that are saved on the stack. So if you pick a large enough value of n, even when you're running scheme, if it's not optimized and you're running scheme, then what is going to happen is eventually you will blow out of stack memory and you'll get a stack overflow error. So it's possible to get a stack overflow error even if you don't have an infinite recursion. You can get it if you've got a function that's written that's doing too much recursion and saving too much information on the stack. So what to do? This is kind of a big limitation, right? Well, one of the things that you can do is you can recognize that for certain types of recursion, it is possible to take that recursion and turn it into something that is stackless. And this is actually, this summation is an example of something, a type of recursion where you can do that. So how would I do that? Well, the principal problem that I have here is that this 5, right, needs to be remembered on the stack so that when I'm done calculating the sums of all these other values, I can take that 5 and use it to compute my final result. So if there was some way that I could avoid having to store that information, maybe what I can do is just get to my result and not have to store anything on the stack. So let's take a look at a way that we could do that without rewriting, without using the stack. So I'm going to take the same sum, and what I want to think about doing is carrying the memory that's associated with the result that I'm building, carrying that with me. All right, so how would that work? Well, here's how I could rewrite that function. Well, you think about it as well. Maybe you can come up with a solution. So, whoops, let's spell define correctly here. Define sum n, and I'm going to call this thing after n some memory. I mean, it doesn't have to be called memory. It could be called accumulator or something like that, because that's really what our n is doing, is we're accumulating values. Okay, and now I'm going to create my con statement again. So if n is equal to, if n is equal to 0, then what I want to do is I want to return some result. So we'll think about what that result is in a second. If n is greater than 0, then what I want to do is I want to return sum of n minus 1, so n minus 1. And what I'm going to do is I'm going to pass in to sum the result that I've calculated so far. All right? So that's what memory is going to be, it's the result that I've calculated so far. That memory is what normally, it's not even what we're storing partial values of expressions on the stack. So what this memory is going to be is a partially computed result. All right, and so that is going to be memory and n added together. So that's the partially computed result. I think I just have to put and then just need a little square bracket here, and I'll have completed that. That ends my conditional, and that ends my define. Okay, so why don't we trace this and see if we need to remember anything as this executes. So we'll call sum with 5, because we want to sum up the numbers from 0 to 5. And we're going to pass an initial result, or the initial value of the memory, of 0. That is going to trigger a call to sum 4 with the value of memory plus n. Memory's current value is 0. and the value of n is 5. So when we add that together, we're going to pass in 5. So we're going to call sum 4, 5. That sum 4, 5 is going to trigger a call to sum 3. And then that value in memory, the second argument, is going to be 5 plus 4, which is 9. That's going to trigger a call to sum 2. And that's going to be, the second argument is going to be 9 plus 3, which is 12. And then that's going to call sum 1. And that's going to trigger the computation of 12, which is the memory that's being passed into sum 1, plus 2, which is the value of n that's being passed in, to sum 2. And that's going to give us 14. And then our final call, the sum 1, is going to trigger a call to sum 0 with the value of 14 plus 1, or 15. Now let's take a look at this final call to sum 0. This is going to trigger our base case and stop the recursion. So the code says up here, if n is equal to 0, what should we do? I left a box here. Well, we're going to return memory. So that's what we're going to do here. We're going to return memory. And so the value of 15 gets returned all the way back up. We return until we end up with the sum 5, 0. And we return 15 as the return value sum 5, 0. And so the result is, when this is all executed, the answer is going to be 15. That's what gets returned. Now here's a question. How much work is being done on the stack, or how much space is being occupied on the stack? Well, the answer is, okay, there's two answers. There's the strict answer, and then there's the real world answer. Okay, so the strict answer is, even though we don't have to remember anything on the stack, it's possible, depending on the implementation of Scheme, that you could have to remember, we don't have to remember any values on the stack. It's possible with the implementation of Scheme that each caller would have to, each called function would have to remember the stack information for the previous caller. And even if that's just how to get back to the previous caller. All right, so that's a possibility. But this is such a common form of recursion, and it has a well-known problem that it can eat up a lot of stack space, that there are optimizations that are typically put into Scheme implementations that recognize that this particular type of function calls are really pretty stackless. All right, the only thing we have to remember is that we're just calling the same function over and over again, but we're not storing anything when we're calling the same function over and over again. So if that's true, then once we reach this value, we don't have to, or as we're building up to get to this value of 15, we don't have to be storing stack records to walk us back through the previous calls of sum. So this is an example of stackless recursion. And because it's stackless, it means that the order, the amount of memory that's used by it is on the order of 1, just like the for loop that we looked at, the Java or C++ for loop. So we've got stackless recursion. That's really great, and that'll perform really nice from a performance standpoint as well. Another interesting feature, so this is stackless recursion. Another thing about this particular type of recursion, if we look back at it, is there's no branching. It's just a method calling a method calling a method calling a method over and over and over again until we finally reach a result. Okay, that happens here, and that also happens here. So there's no branching here. So the fact that there's no branching, the fact that there's no memory storage, which allows us to make this stackless, This is a particular type of recursion that's called, I mean, I called it stackless, but it's not really stackless recursion, it's just stackless. It's called tail recursion. So this is tail recursion. Okay,